Okay, class, this video lesson is going to be an overview of the different ways in which we name chemical compounds. We have quite a few different situations in which we're going to find ourselves needing to either give a name, which is nomenclature, or it could be the chemical formula from the name. We really need to be familiar with names and formulae well enough that we can interconvert with ease. So in this lesson, we're just going to go through each of the different categories. I'm going to start with ionic compounds, and the simplest type would be the binary ionic compounds. Okay, binary ionic compounds have, as the name suggests, two ions, or at least two elements, maybe would be more correct, two elements in the chemical formula. It could be more than two ions, depending on the ratio. And what we need to keep in mind with binary ionic compounds is if the metal is multivalent, we need to know what those are, okay? Now, back in grade 10, you were introduced to positive and negative ions, the cation and the anion, and the charges. And we've been working with those enough in this course that we don't really need to look at patterns and trends. We could look at a particular element on the periodic table and know that if it's, for example, a group 3 element like aluminum, it's going to have a positive 3 charge. If it's a group 2 like calcium, it'll have a positive 2 charge. If it's a group 1 such as sodium or potassium, it'll have a +1 charge. We have the halogens, which are group 7, and those will have -1 charge. And then we have the group 6, which have -2 charges, and finally the group 5 have -3 charges. And these are according to the bonding capacity of metals and nonmetals and the number of electrons that are either accepted or given away. Now when we get into, for example, the elements such as iron, manganese, mercury, gold, many others, we find that two possible charges are often, or even more than two possible charges, are with the element. And we look at the periodic table and we'd be able to look up the possible valences or charges. We can, with a detailed periodic table, find lists of the common ion charge, which would be the first one listed, and then other ion charges. So we need to be aware of those. All right, so this one here shows the names, the classical names, and the IUPAC names. We want to really focus on the IUPAC system, which is the International Union of Pure and Applied Chemists. So worldwide, chemists name and write chemical formulae using this internationally recognized system. So the classical system was a little bit different. It used suffixes that indicated the valence, and this only worked when the element had two possible valences or ion charges. The classical system, therefore, is fairly limited because there are other metal elements that may have three or more possible ion charges. I'm not here today to explain why it's possible for these multivalent metal ions to exist, but it certainly suggests a real complex electron arrangement in some of these where there are different possible configurations, and each configuration has a different number of electrons that would be lost. Okay, so that aside, for bivalent, which are two possible valences, so for bivalent metal elements, these are the ones that we can take note of. The classical system is the simple us or ic. The OUS is the lower of the two numbers, and the ic is the higher. Okay, so the lowest and the highest, although relatively speaking, we're only referring to two numbers. Okay, therefore, lead, for example, would be plumbus or plumbic. That'd be the classical name. In the IUPAC system, we would use lead 2 for the 2+ form, or lead 4 for the 4+. All right, so the IUPAC system is much more inclusive because we can look at elements that would have more than two valences, and we would just need to know the Roman numeral that corresponds to the valence. So know your Roman numerals. So 4 is IV, 5 would be V, and then anything below that, 3 and below, is just that number of I's, capital I. Okay, so a key point here for two compounds that contain the same metal element, but with a different valence, both the compound name and its chemical formula will be different. For example, Au3N and Au3N2 are both possible compounds containing gold and nitrogen, and one would be named gold 1 nitride, and the other one would be named gold 2 nitride. The classical system, we would call it orous nitride and auric. And these labels still sort of find themselves on chemical bottles in high school labs and maybe in the workplace. So it's helpful to be familiar with the two systems, but the IUPAC is generally recognized as the one that is recognized worldwide. All right, the other part that goes together with binary ionic compounds is the crossover rule. The crossover rule was introduced in grade 10, and the crossover rule allows you to, given the valences or the ion charges of the metal and nonmetal ions, predict the chemical formula. And so in this case, the steps are write the symbols in order. Metal always goes first. Write the valences above the symbols. You don't need to show the charge. You don't need to show that it's +2 for magnesium and -1 for chloride, but you just show the numbers. And then the crisscrossing of the valences produces the subscripts. If necessary, we remove highest common factor, which is fairly rare. That might happen in the case where we had, say, lead 4 and oxygen. And if we were to crisscross those, we'd get Pb2O4. And remember the crystal lattice, it's the lowest ratio of ions, so we wouldn't say that there are 2 lead 4 plus ions for every 4 O2 ions. We would say that the ratio, the lowest ratio, is 1 to 2. Or just simply PbO2 would be the correct chemical formula for lead 4 oxide. Okay. So what this ensures is that we have the correct number of cations and anions, or positive and negative ions, to ensure that the number of electrons lost is equal to the number of electrons gained. So once you have confidence in the crisscross rule, you can use this to produce the chemical formula from the known elements in the compound. This handout here is part of your package called Writing Formulas for Binary Compounds. You can apply that throughout to either get the chemical formula from the element. On the other hand, we have the names and the chemical formula that comes from that. Now you notice in the second column, these are all binary ionic, and they're also compounds that don't contain multivalent metals, because we don't see any Roman numerals in that second column, so we take that to mean that there's only one possible valence. We would not need to call calcium nitride calcium 2 nitride, because calcium can only exist in the +2 state. All right, so we would be able to say calcium nitride is Ca, and we could use the crisscross rule if we wanted, or we could just look at a balance of charges. We know that for calcium at +3 and nitride at negative, or +2 rather, nitride at -3, we would need 6 electrons gained and 6 electrons lost. So calcium loses them 2 at a time, so we'd need 3 of those ions to lose 6 electrons in total. Nitrogen gains them 3 at a time. We would need 2 of those nitrogen atoms, and the result would be a calcium ion and nitride ions in the ratio 3 to 2. So we can use the crisscross rule, or at least balancing of charges, to help us get the chemical formula. Alternatively, we could have just taken Ca and put 2 here and 3 there, cross them over, and we would obtain Ca32 N2. So that's to be worked on in class. I think that's all I'm going to look at for the binary ionics and the crisscross rule. So just be familiar with which specific elements may have multiple valences, and when in doubt, just refer to your periodic table. All right, this piece of paper here is also part of your package, and this gives you a little bit of practice with both the classical us-ik method and the stock system. You'll notice in all of these cases, these are all binary or bivalent metal elements. So all of the metals that are in these compounds have exactly two possible ion charges. Ferric oxide. The stock system, or more commonly called the IUPAC, would be iron 3, because it's +3 state, oxide. Okay, so refer to the table. A little bit of reasoning involved here to try to determine the charge on the metal element, but in this case you can reverse the crisscross rule quite effectively, and that will give you the charge in most cases, unless it's been reduced. You have to be careful with that. The best way would just be to approach the chemical formula and look at the charge on the non-metal. So for example, sulfur is -2, and iron therefore at a 1-to-1 ratio would be +2. So this would be iron 2 sulfide, to stick with the iron as an example. And in the classical system, this is the lower of the two valences, so this would be ferrous 2Rs sulfide. All right, so that's us-ic method. You're more responsible for the IUPAC, but I just introduced the us-ic just to show you that there was an older system that was in use before the IUPAC system came into being. With the names going to the chemical formula, again there you can use the crisscross rule as we did before with the binary ionics. All right, so going back to the overview here, so with just closing out ionic compounds, we need to be aware of ions and their charges. Also for compounds containing a polyatomic ion. If you've had a chance to view the video polyatomic ion flashcards and you've received the package, there is also some memory work with polyatomic ions. So I would encourage you to continue to work through that and try to memorize as many of the parent names as possible. And then now we need to also add to those the rules that allow us to connect the parent name to some of the related ions for that family. All right, so here are the names. The naming system for the oxyanions. So these are negatively charged particles. They're anions. They have oxygen in them, so we call them oxyanions. We need to know the base or parent anion. Those we memorized. Table 3, page 95 is given in the text. I've also included a copy of several of the tables from the textbook on your handout package. So you have all the polyatomic ions there. The main ones that we need to remember are the ones that end in 8, and then we can look at these rules here to help us understand how we connect the parent to these related ions. So if we have the base ion known and we add additional oxygen atom or atoms, the most likely situation is we add one more oxygen atom. The charge isn't changing for these. We could explain that in class if any of you are curious about how the charge doesn't change when you're adding more oxygen atoms. But for the 3U's, you've got lots of options with coordinate bonding. So we're talking about the same charge as the parent ion. Additional oxygen atom would be per. One fewer is ite, and two fewer is hypoite. So for example, if we look at our table here, we see that phosphite would be actually, some of them, the oxyanions are not included. Here would be an example: chlorate, chlorite, hypochlorite. We have iodate. We don't have iodite. They don't include many of the related ions. We have sulfate, SO4, 2 negative. We have sulfite, SO3, 2 negative. When hydrogen is brought into the ion, the charge usually changes by 1, 2, or possibly 3 values, because we're changing the number of electrons which are needed from other elements to satisfy all of our orbits. When hydrogen is present and can share electrons, we don't need as many electrons transferred into this charged group. So for every 1 hydrogen that's in the chemical formula, the charge will be 1 less negative, representing 1 fewer electron pairs that's needed in the formation of the ion. So it'll take some time to get used to some of these oxyanions as well as the ones that have hydrogen in them. That's why I encourage you to look at the polyatomic ion flashcards video. Okay, I try to wrap up this section on ionic compounds. Before I go on, I just want to remind you again, you have this resource table 3, which is in your textbook, and you have that in your handout. I've also given you a worksheet here, which I created last year, and I found that there's so many polyatomic ions, and sometimes students think they have to memorize them all, but keep in mind that there's some ways that we can predict the chemical formula as long as we've memorized a kind of a core of parent ions. But in this activity, the challenge here is to give the chemical formula, provide the name, and also give a formula that the ion may be found in. So sulfite, I'm looking at SO3 -2. That's its name, a chemical formula that contains sulfite. So I want to try to use at least 5 metal ions from each of groups 1, 2, and 3. So let's use something a little bit creative from maybe group 3. So let's say thallium. The bottom element in group number 3 is thallium, chemical symbol Tl. Let's look at the chemical charge on thallium, and in this case it looks like it's actually bivalent. So we could write the chemical formula for thallium 3 sulfite, and in this case Tl, thallium, has a valence of +3, and it's going to require 2 sulfite ions because it would collectively give away 6 electrons. And the sulfite, not a lot of room here to fit this in, but the sulfite SO3 to negative, there would be 3 of those. So you're going to have to use a fine point pen, or a pencil would be fine as well. But so that would be an example of the chemical formula that contains sulfate. So keep referring back to this practice sheet. What I find is if students don't get a real good grasp on naming and chemical formulas, chemistry is pretty miserable for you because you're writing all kinds of chemical equations. It's not the chemical equations that we're trying to write, it's what's going on and what type of reaction is it and what are the masses of reactants and products. So you really need to spend some time on this. I've given you a whole lot of worksheets because of the importance of this topic. So spend time, and we'll be having class time for this as well. But here's another example of a worksheet that just assesses your ability to work with a lot of different type of ions and making sure you can name them, making sure you can put them in a chemical formula, and that's one you can continue working on in your package. All right, so let's move on to the other types of compounds which we need to name. We've seen the oxyanions. Another category of compounds is called hydrates, and they're pretty simple to name. You know, the ionics, if they're binary, they end in IDE. If they're polyatomic, they end in ate or ite, or maybe something different depending on the rule there that applies. Hydrates are typically ionic compounds that have bonded water molecules in them. Copper 1 chloride dihydrate is an example. There's a mistake in my chemical formula there. I can just see right now because di suggests 2, and in fact that would represent 2 bonded water molecules. So the chemical formula for copper 1 chloride dihydrate would be CuCl. So there's 1 copper plus 1 ion for every chloride ion, but there are also 2 water molecules as part of the crystal. Now they can be driven off or removed from the ionic crystal if the solid is simply heated. So we may do a little demonstration of this, or you may have a chance maybe to use your Bunsen burners in class and see what happens when you heat a hydrated compound. Not all compounds are hydrated, but quite often there's a color change associated with them. So we'll look at a couple of clips here just to show how this can be useful.
When the hydrated compound, copper sulfate pentahydrate, is heated, the water molecules associated with the ionic solid are driven off, leaving copper sulfate with no associated waters. This compound is called anhydrous copper sulfate.
All right, anhydrous referring there to no hydrate or no water molecules. So the color change that takes place usually with the removal of the hydrated water molecules can be one way of distinguishing one type of compound from another. And the color change is often used to detect the presence of water. For example, anhydrous substances, when water is present, when they're exposed to water, will undergo a color change. So cobalt chloride test strips can be used to detect the presence of water vapor in a chemical reaction, so that's a useful property. You may have seen those used before. The little wee white strip, and then when water vapor is present, then it'll turn blue. Okay, and this second clip just gives another application, which is invisible ink. You may have played around with this as a young kid and seen that you can write a message on a piece of paper, and then when it's heated, the message is revealed. Let's have a look.
Our invisible ink contains hydrated cobalt 2 chloride. Heating the paper drives the water from the compound. The remaining anhydrous cobalt chloride is blue.
Okay, so worksheet 2.5c is lots of naming ionic compounds with binary ionics. You have some polyatomics, and most of those, by the looks of it, don't include multivalent metals. When you look at worksheet 2.5e, you'll see a good variety there as well, where you have name or a chemical formula. You will see some multivalent metals there. You will see some compounds, such as in number 1920 and the name in 24, which involve water. So the other category of compounds which I want to look at here just briefly is hydrates. Hydrates are, as we saw in the video here, have special properties, and the naming of these just involves the prefix, and you have a reference sheet here in your package where the prefix, similar to binary covalent, as we'll see shortly, ranging from 1 unit all the way up to 10, needs to be inserted into the name. So when you get to that worksheet there in 2.5e, you'll see, for those 3 questions at least, the rules will need to be applied for that. Okay? And let's have a look at binary covalence. So with this type of compound, we're going to be just looking at a simple prefix system. So in your package you have, which is applicable to both acids as well as binary covalent compounds, the prefixes from 1 to 10 that would be attached to the element names. And just going back to our overview sheet here, just to include an example, we could think of some that we've seen in class before, such as PCl3. So what is PCl3? Well, it has 1 phosphorus and 3 chlorines. It's non-metal, so it's a molecular compound, covalent bonding. The ending is IDE, so it's the same as binary ionics. The only difference is that with covalent compounds, we actually indicate the number of particles, in this case the number of atoms of the second or the first nonmetal. The only exception is we don't use the word mono in the first element's name. So this is not going to be mono phosphorus trichloride, it will be phosphorus trichloride, PCl3. So again, those ones are quite simple to name. You will find a few in some of the worksheets, probably just towards the end. I think I'll just mention now that worksheet 2.5G, common chemicals, includes some moleculars which have a common name provided or an IUPAC name. For example, ammonia is given, but ammonia's chemical formula is NH3, so it could also be called nitrogen trihydride. I would actually say ammonia is really the common name for NH3. I think that should be in the second column, not the IUPAC column. Ethanol is a special type of chemical group called alcohols. We have ozone, again that would be a unique name also for an element. So as you go through this one, you'll look up on, I think, page 634 in the back of your textbook will help you fill in this. Just give you some connections to some compounds you'll encounter in the workplace. The last category of chemical compounds that we want to be able to name are acids and bases. They're named differently, but I lumped them together because collectively that's a unit of itself that's usually studied in chemistry, acids and bases. These tables are from your textbook as well. I didn't include them in your package that was given. However, they're fairly simple to name. In the case of binary acids, where there are only two elements involved, if it contains hydrogen, you can be sure that it's an acid. And we saw that with citric acid, and saw that it had conductivity as well, because the molecule ionizes when it is mixed with water. So with binary acids, the classical names are different, but just sticking with the IUPAC name as being responsible for that, they're quite often mixed in water, so they begin with the word aqueous, and then hydrogen if there's a single hydrogen, or even if there's two hydrogen atoms, the name is aqueous hydrogen, and then the ion that follows ending in IDE, as we would name it for ionic. Okay, so binary acids are quite simple. Oxyacids are those that contain oxygen, and they're just as easy to name. In this case, we would name it aqueous hydrogen, followed by the name of the oxyanion. And I made a mistake. I noticed, I picked up, I went through the textbook, and it seems that regardless of the number of hydrogens, the prefixes are not used in acids. So what's going to distinguish an acid is the presence of hydrogen at the beginning of the chemical formula, and then at the beginning of the name, the word aqueous. So going back here, I just made a correction to the name for H2SO4, which is commonly called sulfuric acid. The IUPAC name would be aqueous hydrogen sulfate. Would not name it as if it were a molecular compound, dihydrogen sulfate like that. We would just name it aqueous hydrogen sulfate. The reason why we don't name it using a prefix system, although it contains non-metallic elements, acids universally ionize in water, which means that what's more relevant in the chemical name is the ions that are going to be formed, the hydrogen ion, the sulfate ion. So we don't use prefixes, although you might look at it and say, well, yes, but it's non-metallic elements. It's an acid. It's named differently. And the last part of that category of acids and bases are ionic hydroxides. They're dead simple to name because they contain the polyatomic ion OH negative. They're named just as if we were naming an ionic compound. The only difference is, be aware that the hydroxide ion is the representative basic ion for the pH scale, and again, they're typically aqueous, although they do come primarily in solid form. So we don't use the word aqueous in the name, we'll just call it barium hydroxide in the case of the one mentioned, shown here. Okay, barium hydroxide. All right, and that pretty much wraps up the different categories. We have lots of time in class to work through these, and I encourage you to really spend some time with your memory work. The assigned questions are the package, and then there's additional questions in the textbook for both groups on pages 97 to 101. Optional extra practice is also given there. And again, if you have difficulties with some of this because there's a lot of new content and things that you haven't memorized before, just be patient with it. You'll have reference charts throughout the chapter, and by the time we get into the quantities unit, the expectation will be that you have that memorized, but there'll be a little bit of time for you to figure it out. Okay, so we'll see you in class tomorrow.